Hi everyone, my name is Fiona Wong and I'm a Senior Communication Manager at DFINITY Foundation. Thank you so much for joining our workshop. Today's topic is Build an Encrypted Nodes Dapp. We have our speaker, Arshavir Ter-Gabrielyan, with us. He's going to kick things off with the workshop, and I'll be monitoring the chat for questions. We will save the Q&A until the very end, so feel free to leave any questions if you have. This workshop is being recorded and is going to be published on YouTube in the very next few days. Without further ado, I'm going to hand it off to Arshavir. Arshavir, feel free to take it away.
Thank you, Fiona, for the introduction. So, firstly, I wanted to mention the purpose of today's session, which is to demonstrate one of the example dapps that we have developed at the DFINITY Foundation in order to showcase some of the features of the IC. In particular, we're interested in confidentiality, and we're interested in a Dapp that supports multiple user devices. So our user is depicted on the left part of the diagram, and we assume that they can connect to the Dapp using some device, such as a laptop, for which they have access to a web browser. And inside the web browser is the user interface of our Dapp that looks more or less how you would expect. So since this is a note-taking application, we have a list of notes on the screenshot. And then, of course, there has to be a backend for this Dapp, which is implemented as the purple canister depicted on the right part of the diagram. And the canister is hosted entirely on the IC, so no databases are required or any services that are not run on the IC. In addition to this, the encryption part of the Dapp happens exclusively at the front-end side. And this achieves the following. This allows us not to trust how the Dapp is written. From the user's perspective, there's no trust that has to be involved in this. And in particular, this is important because the user cannot guarantee that the Dapp is not updated in a malicious way, even if it was reliable, trustworthy before. So since we're talking about multiple potentially supported devices, how do we synchronize between them? Well, in addition to this, the problem is even more complex because we can have, of course, multiple different users. So first, to authenticate the users, we decided to use the Internet Identity Canister, which is an existing service, external service from the perspective of the architecture of our encrypted nodes Dapp. The Internet Identity Canister allows us to authenticate the users, but then what is the information that we actually store in our encrypted nodes canister? Well, of course, we need to have the collection of nodes, which in our implementation, we hash by user and node ID and represent as text. And this is supposed to be the encrypted text because only encrypted content should be stored in the IC canister in our scenario. And then there's a next node ID, which is essentially a source of generating fresh identifiers for our nodes. And in order to synchronize the content of each user across multiple different devices, we also have an additional devices data structure that hashes by users. And for each user, we can have conceptually any number of devices, which are represented throughout their public keys. And these are depicted in orange on the diagram. So for instance, here, Alice may have 3 public keys registered associated with her devices, A, B, and C. And in order to be able to decrypt the content from those devices, there has to be a synchronization of a shared secret. And for that purpose, we also need in our canister to have the shared secrets that are associated with the registered devices and that are going to be explained later on. So this is a high-level overview diagram for how the architecture of the Dapp is organized. But let me show you how it actually works. For that purpose, I'm going to open a web browser and navigate to the address of the Dapp. So for this part of the demo, I need to have a physical token through which I can authenticate. And since it seems that my token is currently not plugged in to my laptop, I'd ask you to give me half a minute to bring it. Okay, so I found the token, and this is a hardware device that looks a little bit like this, and you can plug it into the USB port of your laptop. And this is required to authenticate using the internet identity. So I'm going to save my identity anchor, click authenticate, and after this, I touch the physical token on my laptop that generates a random sequence that is used in the authentication sequence. And in a few moments, we should be initialized. Okay, so now we can see the user interface. So if I stretch the screen of my web browser a little bit, and what we see here is the interface for adding new nodes. So I can type some text here and potentially add text to it. And then click Add Node. At the bottom of the screen, you see that there is a disclaimer. So an important message from the DFINITY Foundation is that our example dapps, although are useful and deployed to the mainnet, but they have a lot of caveats in terms of how they're meant to be used. And in particular, there are some limitations to these dapps because we wanted to keep them simple enough for new IC developers to be able to quickly get into them and derive inspiration and find solutions to common problems. But of course, if you're developing a production-ready dapp, then there are still many other usability issues that you would like to address that should be addressed before you advertise your service as entirely production-ready. So let me add one more node. And after that, we navigate to the screen that shows the nodes that we currently have. So this one I had from before. I can also remove the node. The reason why it's taking a couple of seconds is because all of this runs on-chain. So you have to remember that there's a consensus mechanism in the background. Now, in order for us to demonstrate how different devices could be synchronized, I will simulate a second device using another web browser. So here I will refer to the left web browser as the left device and the right web browser as the right device. And again, I hit the authentication button. And I'm using my physical token to authenticate myself throughout Internet Identity Canister. While this is happening, you can see that there has recently been another device associated with this account on the left. And on the right, you see that there's a synchronization process. And now we're logged in, and we can see the same list of nodes that we've already observed on the left device, right? And now we can also see that if we go to the list of devices in the right device and in the left device, and these are going to be associated with two different identifiers. In a realistic production scenario, we would also have a feature for associating user-defined aliases, such as the names of these devices for readability. But for simplicity, we're not doing this here. So these are automatically generated identifiers. And now another thing that we can do at this point is, of course, we can remove some of the devices. And in particular, here we have 3, even though I only showed how I logged into 2 different web browsers. That's because I had another device associated with my account from before. And we can see that it's this one at the top. So if I hit this bin button over here, then we will remove that device. And you can see that this change has propagated also from the right device, where we initiated this step, to the left device too. And if you're curious what's happening if we try to remove one of the devices that is currently logged in, and let's see what happens. So I hit remove device from the left device, and the right device has been forcefully logged out as expected. Of course, if we now re-authenticate using Internet Identity once more, then we can add the same device back again. Okay, so this was the demo of the user interface. Now, let's talk a little bit about the structure of the repository and have a go at the implementation of this encrypted nodes canister. So all our example dapps live in the DFINITY/examples repo on GitHub. And I'm going to open this repo in VS Code. A second. So here, if we explore the structure of the repo, then you can see that at the top level we have a Motoko and a Rust subdirectories. And today we'll mainly talk about Motoko because we don't have time to explore both. But our example dapps are implemented in both of these languages, so they have alternative implementations, and this allows you to compare, how well things could be written or how simply things could be written in each of these languages that we currently support at DFINITY. And in particular, you can see the collection of dapps that we already have here, including the encrypted nodes dapp. Now, the first thing that someone who is exploring a repo typically opens is the README file. And we have quite a thorough README that explains what this dapp is intended to do with a high-level overview, and then, of course, gives you the same disclaimer about how not to use the dapp, and shows the concrete instructions for local deployment. So this is important for developers who want to be able to quickly experiment and have an efficient development cycle. In addition, if you're interested in deploying everything using Docker, that allows you to achieve reproducible builds for your Dapp, then we support that as well in this Dapp, and you just need to export the right value for your build and variable, either Motoko or Rust, and the front-end code is actually shared between the two. And in the second step, for the Docker deployment, you would just need to run the deploy locally.sh script. Of course, there's also the instructions for how to deploy without Docker, if that's what you want. Now let's go into the sources directory and see how that is organized. So here, as I mentioned, there's one frontend that is shared between the two alternative implementations, one in Motoko and one in Rust. So let's look into the structure of the frontend directory. Well, this public subdirectory just has some static assets, while the src directory has the files that you would expect. So our frontend is implemented in the framework called Svelte, and this is written in TypeScript. These are the basic components which implement the widgets of our UI, and then there's a few files that that are associated with the backend of the front end, and those include features such as the encryption for our nodes. So you could take a look at how these encryption services are implemented and what libraries we're using for that as well. But without going in too many details about the front end, I would like to spend a bit more time discussing the actual canister implementation, because that's the part that is really specific to the IC platform. And therefore, let's take a look inside. So what we have here is effectively the main.ml file, which is most interesting for our discussion right now. Now let's take a look at this file. Here, I'm going to assume that you're familiar with programming in general, and maybe you've heard of Motoko, and that this is an actor-based language for implementing canister smart contracts for the internet computer. But I'm not going to explain a lot of more details, and I hope that the discussion still makes sense to you. So here at the top, we basically have only one actor class that defines the main actor of our encrypted nodes, Dapp, where the secondary actor is the internet identity canister that we use as an external service, right? So the first thing that we have here is a bunch of constraints. So these are constants that we picked carefully, such that it's not possible to. So these constants are used as in preconditions of our public API functions in this canister, such that it's not possible to exceed certain limits and go wrong, such as the memory limit that is specified by the WebAssembly standard, and so on. And in particular, this means the maximum number of users that we allow is 1,000. And since this is an example Dapp, we don't gracefully handle the case of registering more than 1,000 users. But in the real production scenario, you would probably need to think of that in advance too. So after all of these constraints up here, we have a few types, such as the principal name, which is simply equal to text, and encrypted node. And this, of course, has the encrypted text as well as a natural number identifier for that node. Now, an important thing here is to mention that although we have encrypted as a prefix for the text field here, our backend canister does not actually enforce in any way that the content stored in this field is indeed encrypted. And encryption, as I mentioned before, it does not happen at the backend side, rather at the front end. So this is just for us to remember what we expect to store here. But of course, it is the responsibility of the front end to ensure that the text is indeed properly encrypted. So I would like to go and explore a little bit more and maybe discuss one or two public API functions that we have in this canister to give you a flavor of how this can be written in Motoko, and then maybe dedicate some time to more interactive discussions and addressing the questions that I think you have, judging from the chat. So let's take a look at the core data structures that our canister stores. So the next node ID is the counter that we use as a source, fresh identifiers for our nodes. It's initialized with 1, and we treat it in such a way that it can only increase. Okay, and this variable has the prefix stable. So if you go into the documentation on smartcontracts.org, then you will see that stable memory in Motoko is a means of persisting the information that your canister is storing across canister upgrades. And if you declare your variable with the keyword stable, then you benefit from an automatic way of restoring or persisting the data that is stored in this variable. So we wouldn't need to do anything manually. The language takes care for us in this scenario of canister upgrades. This is important because you don't want your users to lose access to their data after you upgrade a canister to a newer version. So an important practical consideration there. Then nodes by user is implemented as a hash map. It hashes principal names to lists of encrypted nodes, which represent the collection of nodes per user, right? So hash maps are one of the types provided by the Motoko standard library. And this you can see if we scroll all the way up, then we're importing map from a library that is called mo::base, and everything that starts with mo:: is part of the standard Motoko library. So if you're interested in the documentation for the standard library or for the Motoko language itself, then there's a thorough documentation on our website, smartcontracts.org. And for instance, here you can see that there's a page that describes hash map. And on the left side, you can see that there's a lot of different data types that are provided by the standard library. And you can pick those that are most efficient for you. But you have to keep in mind that some of these types are stable in the sense that they can automatically be persisted across canister updates, while others would need to be serialized using so-called upgrade hooks. But we're not going to go into details about that. you can explore them at the very bottom of this main.mo file, where we implement the upgrade hooks for the encrypted nodes canister. Okay, so for the list of users, we also use a hash map. And it's hashing principals to structures of type user store. So if we go to types.mo, we open it side by side here, then we see that there's also a few types that we factored out into the separate file. Okay. Now, the stable users is a representation of the same thing in a way that can be easily serialized. So upon upgrades, this is what we use as a buffer to serialize the values from this hash map of users, and then deserialize them back, creating a hash map which is more efficient to access. Now, this users invariant is a Boolean function that we use in order to ensure that the properties of the internal state of our canister are sane and respected. And in particular, if we're interested in the number of users, then we could compute them in two alternate ways, right? We could take the size of nodes by user, but we could as well take the size of users. So there's this invariant that we're checking here at runtime that enforces that this is actually always the case, and these two structures are synchronized. So is user registered can be computed using simply the fact that a registered user must have their principal as a key in the collection of users. And then we have another function called isIdSane that demonstrates how we use some of these constraints that we discussed at the beginning of the file. In particular, there's a course condition, but since Motoko supports unbounded integers or unbounded arithmetic, we need to make sure that the front end does not request a node with an identifier that is so large that it takes up all the memory of the canister just to store that one number. That would be an absurd scenario, but also a potential angle of attack from a malicious front end. And here, the point is that the backend also should not trust the front end, because anyone in principle who knows how the public API of our canister is organized could implement their own front end for our encrypted nodes canister. And so this is a way of ensuring that IDs are the value of IDs are relatively sane. Okay, so without discussing all of these helper functions that we have here, let's go and see how some of the business logic is implemented. In particular, so I'll close this file to leave more room for the main discussion. This is the public API function called addNode. You can see that it takes an additional color parameter that gives us the principal of the color, and the color could be viewed as another actor in the system that invokes the addNode function, and therefore the result type is async, so it's an asynchronous type, and the beginning of this of our public API functions typically has some preconditions, right? because we don't want to perform a lot of heavyweight computation before we actually checked that it's okay to do so. In particular, we're checking that the anonymous principal, so the anonymous user or an anonymous user cannot invoke this function, which is a way of saying that only registered users may use this service. And then we also assert that the size of encrypted text is within the bounds that we constrain. And this is also needed because we want to protect the canister from attacks from potentially malicious or erroneous frontends that could invoke our public API functions and pass any input arguments that satisfy the corresponding types. So after we check that these basic requirements are satisfied, there's a debug print. So this would appear in the web browser log. And then we extract the principal name for the caller. And then on this line, we create a list of encrypted nodes. Using the nodes by user for this principal name. And so what this code does is it checks whether the principal name is present in the nodes by user collection. And alternatively, it initializes an empty list. So this would happen if this is the very first node that the user is attempting to add. And so once we obtained the current list of nodes that this user has, we now assert that the size of this list is strictly less than the maximal nodes per user constraint. And this is necessary such that when we add a new node to this list, which is the purpose of this function, we're still not going to exceed the maximal number of users that this user, the maximal number of nodes that this user would have. And of course, even though I mentioned that it's good to check the preconditions under which computing this function is meaningful, sometimes it is not possible to perform all the required assertions at the top, although that's generally, as a rule of thumb, that's a good idea to try. So here we have to assert this condition in the middle of the implementation of the function. And so I wanted to mention that if an assertion fails, then the function traps, and the semantics in Motoko are such that a failing assertion causes the computation to be completely reverted. So this is a relatively safe scenario. It's not going to cause the crash of the entire canister. So after we ensure that this is okay to add more nodes to this particular user, we create the node by simply assigning the identifier of this node to the next node ID and assigning the encrypted text to the one provided by the client. And of course, we need to increment the next node ID because otherwise we would not have unique node identifiers. And finally, we need to put the newly created node into the list of nodes for this user, for which we perform line 190. Okay, so let's go into one more public API function, in particular, the one that, so let's see which one would be most interesting, because we don't have time to discuss all of them. So why not this one? Deleting a node requires the node identifier as an argument. And in the precondition here, we check analogously to what we did for adding nodes. We check that this cannot be the anonymous principal and that the user is indeed registered. And then we use our sanity check for the identifier value before we actually use the identifier to perform any lookups. The principal name is extracted from the caller, and then the nodes of this user are extracted in a way which is very similar to what we've seen before, after which we simply we simply put under the principal name a new list that filters the nodes that this user currently holds using this lambda function here, which shows how in Motoko you can write quite conveniently functional styled code. So this lambda function takes a node and it returns true if the node identifier is not equal to the identifier up there as an argument of delete node. And as you probably expect, the filtering function will filter out the node with that identifier. So a design decision at this point is made that we don't raise any errors in case a node with such an identifier has not been found. This would be completely normal behavior, which could be useful in practice if multiple devices, for some reason, try to remove the same node at roughly the same time, then only one of them will succeed, but the others will not cause any failure too. Okay, so now we explored a little bit of the implementation of this canister, and I think this is a good time to look into the questions. Fiona, would you like to read out loud some of the questions?
We don't have any question now, but our beloved developers, please feel free to leave any questions you have to ask Arshavir, and he will be answering your questions. So you can leave your questions in the chat room as well. You can also raise your hand. Okay, we have one question from the chat room. For the rest of you guys, please just be aware of the question in the chat room. Debug can be used as warning or feedback mechanism. Arshavir?
So this refers to the debug state, the debug prints that we have here. Yes. So if I remember correctly, debug prints are visible both in the. So if you deploy your canister locally, then at some point you will have a console emulator that runs the local deployment process, and you will see these printouts there, I think, as well as in the web browser console. So I think they're also sent to the front end, which is a convenient way of checking which API functions were actually invoked.
Thank you. Any more questions?
So maybe I can also try to make my answer a bit more precise, because it's about feedback mechanism. I guess it depends what kind of feedback you're looking for. I wouldn't use them as normal feedback. I would only use debug prints for the development process while you're developing your canister. But the end user would need different feedback mechanisms. Like, you would probably want to have a widget that indicates the status that your canister is in, or something like that, to have it more visual, because I wouldn't expect the user to go into the debug console in their web browser in order to see what's going on with the Dapp.
Thank you as well. That we have another question that you also can check it in the chat room. In the encrypted nodes, when we log in with multiple devices, what will be effect on speed of execution of commands? As we have seen, there is a bit of lag in action.
Mm-hmm. Yeah, that's a very good question. So the bad news is that we have to pay the penalty of having on-chain computation one way or another. And this is something that the consensus mechanism requires. And this is what we have to pay. And this is why you can observe the lag. Keep in mind that the lag is becoming smaller while DFINITY is improving its backend technology. But ultimately, there are multiple computation nodes involved in the consensus. And therefore, we cannot instantaneously obtain changes when we're dealing with smart contracts that work on top of a blockchain. But the good news is that the lag is not so dependent on the number of devices or the amount of computation that needs to be done. Okay, so this means that it's not the bottleneck for scalability of your dapps. It's mostly a concern that you need to think about, like, what information you're processing in one step. Where one step is effectively an update call in terms of the Motoko language. So keep in mind that there are, in addition to update functions, there's also a concept of query functions, which are much faster. However, query functions cannot change the internal state. And query functions could be viewed as an optimization because they do not go through the consensus mechanism, and therefore you cannot validate that the query function actually returns trustworthy results until you wait for an update function to go through consensus and confirm that this query returns. So in that sense, query functions could be seen as an optimization, a very practical one, but you have to think very carefully about the design of your Dapp and how you incorporate query functions. So at the first step, I would recommend only using update functions to ensure that your Dapp is secure, and then try to work on improving its performance.
Thank you. We've got a question that related more to the languages. So Bhavesh asked if anyone have knowledge of Rust and how much effort does he or she need to require to learn Motoko?
Mm-hmm. Well, it's an interesting question. So Rust is also natively supported. So we have a Rust CDK for the internet computer. And therefore, you can use all the features that the IC provides throughout any of these languages without much trouble. So it's generally quite a similar experience on a conceptual level. But of course, the flavor of the implementation in Rust is significantly different. And for those of you who are Rust experts, Rust typically assumes that you're working in a multi-threaded environment in a classical computational model with one node, right? And actors that implement internet computer dapps are single-threaded, and concurrency is achieved through message passing, or through query calls, or through update calls, which are potentially asynchronous. So this is a slightly different computation model, and therefore the Rust type system is sometimes not entirely aligned with the goal that you have while writing your Dapp in this language. Just to give you a quick flavor of how this looks in Rust, let me open one of the source files that we have for the encrypted nodes canister. Yes. So for instance, do we have remove we have remove device. Yeah, so we haven't discussed this particular, or maybe it's easier to discuss one of the functions that we've seen in Motoko, how that same function, that very same function would be implemented in the Rust language. So a public API function would need to have a decorator that specifies its name from the perspective of the public API in the candidate center. But otherwise, you can see that the structure of the implementation is similar. So we have these assertions at the top of the function, which effectively check the precondition of it. And then, of course, the data structures that we use are Rust specific. And you can see these caveats, such as the problem of using global state in Rust, right? Which we require for the next node counter. So you will have some additional code that you would need to write. If you're not familiar with Rust, for this very reason, I would probably recommend to first look into Motoko.
Okay, thank you. Do we have any more questions? We still have 12 minutes left, so feel free to raise any questions.
So until there are more questions, maybe one other thing that I would like to mention is to demonstrate the device synchronization, which is
we don't.
Yes, please.
Oh, it's okay. Please just continue.
So I would like to show the functions that are involved in device synchronization, because this is one of the more advanced features of this Dapp. So the device synchronization logic is implemented at the lower half of the source file, mostly, and it starts. So let's look into, for example, the remove device function, right? The precondition is unsurprising. The specific one here, the kind of device specific one, is that the alias size has to be constrained. And then in order to remove a device, recall that we have the concept of users and user stores, right? So this users collection contains the user store for the user with the current principal, So we obtain the store of the current user. And here we're using this expect function, which is a helper that effectively just implements a trap in case the option returned by this getter is null. So this just saves a bit of coding. So the reason why we write expect here is because under normal circumstances, there must be a user registered with this color and this principal in the user's collection. Otherwise, it doesn't make sense to try to remove a device for a user that doesn't exist. So once we obtain the user store, we perform an assertion on the size of the devices list in this user store. And make sure that there is at least one device to be removed. Otherwise, it doesn't make sense to remove if the user doesn't have any devices, right? And then we iterate through, so option iterate basically just checks whether it's similar to a flat map in some other languages, which basically just checks something, but only in case the value for the option is sum. And what it does is it checks that for the device under the alias, under the specified alias, if we have a device, then we're going to apply this lambda function to that very device. And since the devices are represented throughout through public keys, what we will do in case there's a device under this alias is that we will delete the device with this public key through the ciphertext list of the current user's user store. So after this happens, the remaining devices would need to synchronize. And this is implemented using polling in order to detect the change in the ciphertext list. All registered devices perform polling to the backend canister from time to time. And once the backend canister detects or reports the change, then the shared secret is recomputed. And this is how the changes propagate to the remaining devices, and how the remaining devices would at some point notice that one of the devices has been removed. And as a very last step, we also remove the device from the devices list of this user store that corresponds to this alias name. Okay, so this is a quick overview of one of the device synchronization functions. There's also get devices, which is actually used in this polling mechanism. Get unsynchronized public keys. And then there's also this is seeded function that returns whether the user has at least one public key, which typically happens after the user is freshly registered, after we freshly register a new user. And of course, there's a get ciphertext, takes a public key of a device and returns its ciphertext. And there's a way of submitting new ciphertexts. So this happens after a device polls and detects a change, and then it updates the list of ciphertexts that it maintains, and it sends it to the backend canister for the change to propagate. And then there's a seed function, stores a public key, an associated public key under the an empty user store. So this is what's happening when we register a new user. And finally, we reached the part with the upgrade hooks that I mentioned at the beginning. So these are invoked before a canister upgrade is performed, in which we serialize the internal representation, the hashed representation of our data, such as the notes by user and the user's collections. And the serialized representation is stored in the stable buffers, which are variables with stable type and prefix stable. And after the upgrade, the post-upgrade hook is invoked, where the exact reverse is happening. So we take the stable memory and deserialize it back into hashed representation, which is more efficient for our canister. All right. Are there any outstanding questions?
We don't receive any further questions. Hey guys, if you have any more questions, we have 4 minutes left for the Q&A section. So feel free to raise your question. I don't think we have got further questions.
I see that there's a lively discussion in the chat, but I don't see any questions.
Yeah, they're chatting something based on the content you are sharing. So if we don't have further questions, that I think that we might wrap up today's workshop, that you guys can also check today's video on YouTube later on. And thank you so much for your time. And next week, we'll be talking about Mint and NFT. So see you next week. Thank you so much, Arshavir.
Thank you very much, Fiona, and thanks everyone for joining. Have a nice day. Bye-bye.